Okay, hello everybody. Welcome to our second physics workshop for the summer semester of 2022. Today we're going to be doing some basic problems involving vectors to give you guys some practice working with vectors. I'm assuming if you're looking at this course, you're somewhere in physics where you're starting to utilize vectors and you want to get a little bit more practice with those. But real briefly, I'll go into what a vector is before we start trying to solve problems. So for most of your mathematical career, you've been dealing with quantities, right? Simply a scalar, simply a number. A vector is similar, but it has the additional component that it also gives you information about direction. So a vector is just like the math you've been doing before, but we also have to be careful and we have to note our direction. So that's the main difference. There's some interesting properties about vectors. Some of them we're going to explore over the course of this workshop, doing our little worksheet here. I'm going to dive right in. We're going to start with one-dimensional motion. So our first question is, a car is initially stopped at a light. When the light turns green, the car accelerates rightward at a constant rate of 3 meters per second and continues in a straight line. What is the car's velocity after 8 seconds have passed? So that's part A. And then part B asks us, if the car stopped accelerating and continued at that speed while you ran on foot, could you outrun the car in a 100-meter dash? All right, so we'll answer part A and then we'll take a look at part B. This problem is pretty simple. It's pretty straightforward, but we do want to get that practice with vectors. So let's go ahead and draw out some semblance of the situation. So I'm just going to do a little bit of a, let's see. We want it the other way. Okay. I don't draw the straightest line, so I'm going to try to, okay, so here's our axes right here. I'm going to call this horizontal axis. We'll call X. Pretty traditional. All right, so there's the X-axis. And we learned that the car initially is stopped, right? So let's say it starts right here. I'm going to put a little box. This is going to signify our car. Initially it's stopped, but then what happens? It accelerates to the right at a constant rate. So it's accelerating rightward. They tell us the acceleration is equal to 3.0 meters per second squared. Okay. All right, what other information do they give us? They tell us that 8 seconds pass, or after 8 seconds pass, that's the time that we want to consider. So let's take a look at that. We're going to say that t is equal to 8 seconds. All right. We've set up the situation. I think we understand it, right? The car is stopped at the light. It's going to accelerate. It starts to travel. 8 seconds pass, and we want to know what is the car's velocity 8 seconds after it's passed. Now, velocity is what we call a vector quantity. Velocity is a vector quantity. So that means it gives us information not only about the magnitude, but also about the direction. So we want to know the speed, and we also know what direction it's going to travel. And that's how we need to give our answer. All right. So we're given acceleration, we're given time, and we need to find velocity. Maybe an equation jumps out at you off of your memory, or maybe you want to think about this question and then see if you can come up with anything. If this is a recording, maybe you give it a pause and you see if you can think up what the equation that relates these quantities is going to be before I write it out. Okay, so I'm assuming you've had a go at it. Now, we may recall what jumps out to me is that the final velocity should be equal to the initial velocity plus whatever our acceleration is times the amount of time that we accelerate for. So that is VF is equal to VI plus AT. So let's take a look at that a little bit more in depth. We were stopped at a stoplight initially, correct? So that means our initial velocity, what was it? It was actually just 0. So can I rewrite this again? Let me do it on the bottom of our drawing, maybe. Okay. Oh, let's see. Running out of space on my tablet. Okay. So VF is now just equal to AT, and it's looking like this is really just a problem involving multiplication. Now, we're talking about vectors here, so I should be careful. I'm going to do it in red so that we can see it. We can see it very carefully, or that it stands out more. So these quantities are vectors. They have little arrows over the top of them. That tells us that they're a vector, or sometimes you'll see a vector in boldface. So the velocity has a directional information, right? It tells us the direction that we're traveling, the direction that the speed is in. And so does the acceleration, right? Didn't they say the acceleration was rightward? So both of these are vector quantities. Now time is just counting up. Time is not really telling us a direction. You could say time is always marching forward, and sure, not really relevant to the problem, but we need to identify these vector quantities. And it's a different thing to write this without the arrows and to write this with the arrows. So especially as you're starting out doing these vector problems, try to be very precise with what you write down with your notation. Okay, so let's solve this. Seems pretty straightforward. We can just kind of plug in here. So the acceleration that they gave us was 3.0 meters per second squared. Okay, and that's going rightward. And then we multiply that by how many seconds passed? 8 seconds, I think they said. All right, let's check what happens here. So 3.0 times 8 is 24. Okay, sorry, I keep losing tracking on my pen here. There we go. Okay, so we have 24, and then what are our units going to be? We have meters per second squared times seconds. So one of those seconds cancels out, and we're left with meters per second. And that's what it should be. That is a velocity, so that all checks out. The question is, what is the direction? And the answer is the direction is still positive, right? So we're still going rightward. So we're going to say 24 meters per second rightward, to the right, from our frame of reference. Okay, so we solved it, and now that you're looking at it, basically this is just multiplication, right? It's really, really straightforward, but it gives us a little bit of practice with this notion of vectors and pointing in a direction. So the answer is just twofold. It's 2 parts, 24 meters per second. That's the magnitude, that's the speed, that's how fast, that's how big. And then the direction is rightward. The direction is rightward. Okay, so let's tackle part B. Part B says, if the car then stopped accelerating and continued at that speed while you ran on foot, could you outrun the car in a 100-meter dash? Okay, so this is kind of this is a bit of an intuition check, right? It's just saying, like, how fast is this speed, and could we run faster than that? So 24 meters per second. Personally, spent most of my life in America, so I usually think of speeds for cars in miles per hour. Miles per hour. Okay. And I happen to remember, but always you can do the conversion yourself, and you can look this up, and you can work the conversion. But I happen to recall that if you're converting from meters per second to miles per hour, it's about 2.2 times greater. So 24 meters per second is about approximately, let's say, just do 2 times greater, just to approximate. So let's say it's about 48, to really be in excess of 50 miles per hour, something over 50 miles per hour. So can you outrun a car traveling 50 miles an hour in a 100-meter dash? I cannot. I doubt you can. I seriously doubt it. I'm going to say no for part B. All right, let's get on to the next one. I'm going to copy it over from another page here, so bear with me. Okay. All right. Okay, so I'm looking at our worksheet. Let's copy over the second question. Okay. So this is another question with one-dimensional motion. Let's see if we can squeeze it in right here. All right. This one says, an advanced probe has been sent out from our solar system and it travels a straight line through interstellar space. Okay, so real quick, I'm going to pause here. Because this travels a straight line is already making me think of vectors. And of course, I know we're working with vectors because this whole worksheet is about vectors. But that's something to maybe underline or note. Travels in a straight line. It sounds like one-dimensional motion, right? A line. Interstellar space at a speed of 3.0 times 10 to the 5 meters per second. And they ask us approximately how many years will it take to reach its target, Alpha Centauri, 9.5 times 10 to the 12 kilometers away. Okay, all right. So once again, straightforward, but let's draw our lines. I need to scroll down some more. All right, give ourselves some space for that problem. We'll leave the other one behind. All right, so once again, we're traveling in a straight line. You pick the line. It could be in any direction. You can imagine it however you want. We're only considering the one dimension, so it's pretty straightforward. I'm just going to draw a line once again, rightward, right? Okay. Once again, rightward. We have our space probe is traveling. Okay. There's my space probe. It looks like a potato, so I would build it. Seems good to me. Travels in a straight line through interstellar space. So they tell us a speed. They tell us a direction, right? It's traveling toward Alpha Centauri. So we know the velocity is 3.0. So let's say velocity is equal to, this velocity is a vector, 3.0 times 10 to the 5 meters per second towards Alpha Centauri, towards Alpha Centauri. I'll just say AC. Okay. All right. They also tell us a distance, right? They tell us how far away. So what would that be in terms of our kinematic equations, or just in terms of some of the equations you learned in high school, right? Distance equals rate times time, say. We could use that. But let's use the kinematic equations, show how they fit for just about which whatever. So let's say XF is the final position, and XF is 9.5 times 10 to the, I'm going to say 15 meters away. 15 meters away. So I've done a conversion there. Don't let that confuse you. So we were 10 to the 12 kilometers. And I know there is 1,000 meters in every kilometer. So I went ahead and multiplied to meters. We want to get everything into SI so that our units will work out. We've gone ahead and done that. Now we think if we finish this out here, what else do we have? We have X. Uh-oh. Froze up. There we go. X, I. Let's just call that equal to 0. Let's say we start at 0. Since I know the distance we totally travel is this 10 to the 15 meters. We've accounted for that here. All right. I think that's basically everything we need. So let's write out a couple of equations. You can reference them. Here's the one that you'll see for your kinematic equations. XF is equal to X sub I plus v t plus 1/2 a is acceleration t squared. Okay. It's got a lot involved in it. I don't think we need all of that. How about distance is equal to rate times time, or if I can say in this case, velocity times time. Distance equals VT. All right. So you see T is equal to D divided by V. Once again, we have something straightforward. Okie dokie. Approximately how many years? So we're going to need to do a little conversion in the end here, but let's quickly punch this out on calculator. Uh-oh, where's my calculator? It's okay, we could probably pull one up right here. Calculator. Okay. Nope, this is going to be too annoying. I'm going to grab my actual calculator, TI. Okay, so dividing the distance by the time, we've got 9.5 times 10 to the 15 all over 3.0 times 10 to the 5. I get 3.166 repeating times 10 to the 10 seconds. Oh, that sounds like a lot of seconds. Let's see how many years that is. Let's see how many years that is. Okay. We got 1.33. Nope. 1.6. Sorry. 1.66. Repeating times 10 to the 10 seconds. S. Okay. And I know that there are 3,600 seconds in 1 hour. Okay. This is the same thing as saying there are 60 seconds in 1 minute and 60 minutes in 1 hour. 60 times 60, 3,600. And then in 1 hour, I'm sorry, there are 24 hours in 1 day. Just doing the conversion long form so you can see it. 24 hours in 1 day. And then there are 365.25 days in 1 year. Why did I say 0.25? Because of leap year, once every 4 years. If you don't include that, it's probably okay. You're going to get pretty close. Sometimes people account for leap years, sometimes they don't. Nonetheless, we're just going to punch this into the calculator and we should come out with years. So I'll take the answer we previously found, that 3.166 times 10 to the 10 seconds. And I'm going to divide that by 3,600. I'm going to divide by 24. And I'm going to divide by 365.25. Let's see what we get. I get 1,003, or they say approximately how many years. So let's say they give us about 2 significant figures. So let's call it, let's round, and let's say it's approximately 1,000 years, right? We got 1,003 years. So it's about 1,000 years to reach Alpha Centauri. Takes quite a while. And we were traveling quite fast too, but only a portion of the speed of light. And the distance was pretty significant. So 1,000 years it would take our probe to reach that nearby star. Okay, let's do the next one. We're going to leave off from one-dimensional motion. You got the basic idea of a vector. We're going to start doing component vectors. We're going to break vectors into pieces. And this is where vectors get interesting, and this is where they're especially useful, and you'll solve lots of problems this way. Give myself once again some space. Okay, bringing that down. Don't want that. There we go. Okay, number 3. All right, so it's looking like projectile motion because it says a cannonball is fired from a cannon at an angle of 55 degrees from the horizontal. Upon exiting the cannonball has an initial velocity of 250 meters per second. How long will it take the cannonball to hit the ground? You may ignore air resistance. All right, so once again, let me try and give you guys a drawing. And when you're working these problems at home, and I encourage you to try to work the problem out before me and then watch how I do it and compare our strategies, compare our approaches. But remember to do these diagrams, even if you feel like you don't need one, especially when you're starting out at first. Get good practice clarifying these things so that when the problems get more complex, you don't find them too difficult. Let me see. Can I represent this cannon as this box here? Let's see. No, that's not great. That's not great. Let me try and draw it for you guys. So it says that it is 55 degrees up from the horizontal. So if we take an angle here of 55 degrees, 55 degrees higher than this horizontal line, that's the line that our cannon is firing over. This is the angle that our cannon is firing at. So there's my cannon. And we imagine it fires this cannonball. And we learned that the initial speed of said cannonball is what? It's got the velocity of 250 meters per second. 250 meters per second. So if you think of miles per hour, that's what? That's over 500 miles per hour. Astonishing. Okay, 250 meters per second is our velocity. Now the question that they ask us is, how long will it take the cannonball to hit the ground? And they say, you may ignore air resistance. All right, may ignore air resistance. We're fine to use our simple kinematic equations like you've seen in your mechanics course. Now, let's see right here. I talked about how we're going to need component vectors. I maybe should have drawn a little bit bigger. I think I can give you the impression. So the way that we're going to tackle this is we really don't care how far the cannonball travels, right? We only care how long it takes to hit the ground, which means how long it spends going up and then how long it takes for gravity to pull it back down to the earth, right? It's going to reach some peak height, we know, somewhere, and then somewhere else it'll crash into the ground. We don't really care where that point is. We just care how long it will take until it does hit the ground. So what we're concerned with primarily in this problem really is how much of that velocity is contributing to an upward, is just contributing just in the upward direction. Let me move some of this around. Let's see. Uh-oh, wrong button. Uh-oh. Sorry about that. Okay, back where we were. I was trying to select this and drag it up out of our way. Let me just erase it. We'll remember the 250. Okay. And what I'm going to do now is draw. Let's see if I can't give us a better idea with maybe this. All right. Yeah, that's gonna work. Okay. So follow along with me here. I'm breaking this up into 2 pieces, all right? Really 3 pieces. So the velocity was something like this at that 55-degree angle, right? This blue vector that I've drawn is that 250 meters per second. Okay. And whereas we're trying to find out, what is the portion of that velocity that's in the upward direction? This green vector right here. Right? Because the only thing that determines how long something takes to hit the ground, at least if you're not at like an orbital speed, is how fast you're traveling in the upwards direction, how long it takes for gravity to pull you back down to the earth. So we've got this angle is 55 degrees. You may be recognizing a right triangle. And trigonometry is super your friend here. Whenever you're doing component vectors, it's going to be a lot about finding triangles, especially right triangles, breaking them up, and then using your trigonometry to solve for these components, right? These pieces. Any vector that you take at any arbitrary angles, this angle, whatever your vector is, however it's pointing in space, you can always break it up into some combination of traveling in discrete directions based on some axis. So if we're in 2 dimensions, any vector has some component that travels in the y direction and some piece that travels in the x direction. And we can break those apart and we can find out how much is it going in x versus how much is it going in y. All right. So we're going to do that now. Let's see. We're going to break out our trig. And if it doesn't immediately occur to us what trig formula we should use, we can write out the classic SOHCAHTOA. Remind yourself, SOHCAHTOA. I'll do this just once because I'm sure you've heard SOHCAHTOA a million times. It's always good to recall. Never forget how to use your trig as long as you remember it. So the sine relates the opposite end of a triangle to the hypotenuse. The cosine relates the adjacent to the hypotenuse, and the tangent relates the opposite to the adjacent. So what we're looking for is this quantity. Let's call this Vy. We want to know how much of V is going in the up direction. This is the opposite side. So couldn't we say that the sine of 55 degrees, make sure your calculator's in degree mode when we punch this out, shouldn't that be equal to the opposite over the hypotenuse, Vy divided by 250 meters per second? Sure should. So if we want to solve for Vy, scroll down, get some more space. Okay. Let's move the hypotenuse over to the left-hand side. So 250. Back to draw, please. 200. Back to draw, please. Oop, okay. 250 meters per second times the sine of 55 degrees. That ought to give us Vy. Okay, super duper. Now we could punch this out and we would get some kind of number, but I'm not too interested in doing that yet because I want to find what equation we're going to use this in. You probably guessed it's going to be one of the kinematic equations. We're dealing with some projectile motion here. Which one do I want to use? I want to find the time that it takes for the cannonball to reach the ground. You can look through your list. You can think about it for yourself. The one I'm going to pick is, instead of x, we'll say y. We're thinking about the y direction. Y final is equal to y initial plus velocity initial in the y direction. So that's Vy, right? Vy times t. Okay. Plus 1/2 a t squared. Okay. And then if we look at this a little bit further, we can see that it's starting from 0, right? We'll assume that the cannonball is launched just from 0. Maybe it's really launched from some height here, like maybe a 1/2 meter or something like that, but they don't say that in the problem. We're not too concerned about that. And we want to know when it hits 0. So here's just going to be 0. This is going to be 0. So we've got 0 is equal to Vy t. Vy t. All right. Sorry, my tablet keeps kind of freezing up a little bit. It's going a little slow today. And then 1/2. And I'd like us to think about what is the source of acceleration here, right? The only source of acceleration once the ball has been launched, the cannonball is flying freely through the air. So the only force acting on it is the gravity, right? They tell us to ignore air resistance. So this is just going to be a negative g. The acceleration is just negative in the direction and equal in magnitude to the little g, acceleration due to gravity. And this is times t squared. All right. So you may recognize this equation is of a quadratic form. We have t and t squared. It's all set equal to 0. So if I move this around, I hope it doesn't confuse you too much. I'm going to do a couple steps at once so we can get through some more problems. Pause it and think about it if you need to. So this is 1/2 of 9.8 meters per second squared. That's the value of little g. And I'm going to move it to the left-hand side. So I'm going to say 4.9 t squared. So I flipped it to the other side. I took away the negative. I divided by 2, and I wrote g as 4.9. So you can see that number there. And then we're going to move this also to the left-hand side, the Vy. And remember that we found that Vy was equal to 250 meters per second. 250 meters per second times the sine of 55 degrees. 55. All right. Super. So we're ready, I think, to punch this in. And you have your different strategies for solving quadratic equations, but this is a 4.9 and a 250. So I think let's use the quadratic formula. I'm going to start to punch that into my calculator. So A is 4.9. B is negative 250 sine 55. Remember, it's that whole value. That whole thing is multiplied by t. Oh, and I forgot the t here. This is times t. It's the whole reason it's quadratic. Don't forget. Okay, please let me draw a t. Let's see. Aha, okay. One very ugly t joining us at the party. All right, let's punch this in. So we've got 250. So negative becomes positive, 250 sine of 55 degrees. Am I in degree mode? Yes, I am. And then that's going to be added to b squared minus 4ac. Well, 4ac is going to be 0. There's no c here. So it's just the square root of b squared, which is just b. So it's just, once again, 250 sine 55. All right. We're going to divide that whole thing by 2 times a. 2 times a would be 9.8. And what do we get? We get 41 seconds. The cannonball is in the air for 41 seconds. Wow. Really stays up there, hanging out for a while. But it was launched at 500 miles per hour. So it's sure to travel quite far. And we aimed quite high too. So 41 seconds. I really should say, sorry, I should be a little more precise than that. Let's see, they gave us 3 significant figures. Let me erase. Let's call it 41.79. Let's say 41.8, rounding to our 3 sig figs. 41.8 seconds. All right. Now let me see. Yes, we're okay. I really should have, for you guys, I really should have put a little vector quantity here on G so you guys could see it's in the downward direction, right? We can keep straight with that. This time, remember, is not a vector quantity. It's just a scalar. It's just a number. but we used vectors and we broke them into components in order to answer the question. And that's going to be the problem solving strategy for a lot of your problems involving motion, utilizing component vectors. Okay, let's make some room. We'll go on to the next one. All right. Looks like we got 3 more, so maybe I'll try to speed up just a little bit to get through most of them. If I don't get through all of them, maybe we can work on them at a future time. Okay. 4. Your early ancestor is out on a hunt. They travel 5 miles due east, chasing their prey, then turn and chase it another 3 miles due north. They've become lost, but luckily you arrive in your time machine and have a calculator handy. Oh, good. Lucky for our ancestor. What direction and distance should you tell them to travel so they can return home in a straight line? Okay, so some stipulations. We're supposed to give them directions home, but we need to give them directions to get home in a straight line. So we can't just say, I guess we can't just tell them to go back the way they came, right? We can't remind them of how they got there and just tell them to do the reverse. We need one straight line that will get them back where they were. So let's try to draw out the situation. Again, remember, see how they're giving us a magnitude. You're probably getting sick of hearing vector at this point, but they're giving us a magnitude and they're giving us a direction. So that's a vector. They're keying us in that there's a vector here. Oh, but they start out 5 miles headed due east. Due east is perfectly east, so straight eastward. So that's once again to the right-hand side. They sure do love the right-hand side. I'll draw this out. This should be a straight line. Pretend that my line is more straight than it is. We're headed straight east. Let me do a little compass. We're going to orient. This will be for our whole page in our drawing. Okay, so up is north. To the right here is east. Bottom is south. And to the left is the west. So northwest, east, and south. We travel east and we go for 5 miles, 5.0. And then what do? We turn and we go due north, straight northward. A little 90-degree turn right here. Looks like we're constructing the basis of a right triangle. Okay, you'll see that often. We go for 3 miles due north. And then we want to pick a straight line that's going to get them back home. So it strikes us that the perfect straight line to do that is the one that completes this triangle, right? That's the most efficient straight line path that we could take to get them home. And the question is, what direction do we tell them to head? And how far do we tell them to go, right? So we need to give them the vector. We need to give them the direction of how they can get there. And we can see just by looking at this, they need to go somewhat to the south, right? To cancel out all their motion to the north. And they need to go also to the west in order to cancel out all the motion that they had to the east. But we're going to need to use math. Good thing we came in our time machine with our calculator. So we should be able to calculate this for them. You guys pause it, you give it a go. Pause it, give it a go. So we're looking for two bits of information for them. All right. We need to find this angle. Let's call it theta. We need to find theta. And we also need to find this length, h, this length h. Okay, so let's see if we can do that. We've got 2 bits of information about this triangle. It always pops out in me because you study the Pythagorean theorem and you use it a million times. So when I see an opportunity to use it, I want to use it right away. I remember that when you've got a right triangle here, then Pythagorean's theorem tells you the length of the hypotenuse, right? The length of the hypotenuse. And what is it? It's a squared plus b squared is equal to c squared. So in our case, we get 5 squared is 25, right? 25 plus 3 squared is 9 is going to be equal to c squared. So the square root of this sum should be equal to c. Doing a couple steps at once. Pause it if you need to. I'm just trying to get through this. And what's that going to be if we punch it out on our calculator? 25 plus 9, what's that? 43. Square root of 43. Okay. The square root of 43 is approximately 5.8 miles. So how far will we tell them they need to walk? They need to walk 5.8 miles. That's a pretty good deal. Since they've already traveled 8 miles, we're going to get them home in just 5.8. Nice. But what is this angle? This is very important because if we don't tell them the right direction, they will definitely not make it home with their dinner. That would be tragic. And I guess maybe we wouldn't be here since this is our ancestor. So we need to get them home safe. What is this angle going to be? You guys think about it and you tell me. Trigonometric formulas again. Trigonometric formulas. We have SOHCAHTOA. And we're looking for this angle theta. And we know that the tangent of theta is equal to the opposite over the adjacent. So tan theta equals O over A. All right. So then how do we find theta? Well, the tangent inverse, we'll call this handy trick. The tangent inverse of the tangent of theta is equal to, we take the tangent inverse of both sides, right? Well, pen froze again. Okay. Do my mouse, the tangent inverse of O over A. All right. So on the left-hand side, we're just left with theta, right? That tangent inverse of the tangent is theta provided. And then we can punch this into our calculator. You're going to go and find your inverse tangent function. So tangent inverse of the opposite side 5 divided by 3. That gives us an angle of 59 degrees. Make sure you're still in degree mode, or you can do it in radians if you want to, although maybe your ancestor has a better chance of understanding degrees. I don't know. I found radians a little trickier. Okay. Now the question is 59 degrees in relation to what? In relation to what? Think about that before I give you the answer. So this is the angle that we were looking for, right? If we post our little map on here, this is south, right? This direction over here would be due west. This is to the north up here. And this is to the east. So we want to head straight south, but then we want to turn 59 degrees towards the west from south. So our direction is 59 degrees west of south. Or you might have said it a different way. You could say it's south of west. We could do it the other way. So if you had said, what would it be? This is 90 degrees, 51. So 31 degrees south of west. That would also be correct. Either one you said. Okay, great. We solved another one. Let's get on and see what else we can do. Okay. So that's components. Let's see if we can get some. Let's see what's next. I liked that one though. Okay. Going into some two-dimensional motion. We already did a tiny bit of two-dimensional motion with the cannon actually, but okay. Consider a setup that is similar to question 3. This time a cannonball is fired at an angle 30 degrees from the horizontal with the same initial velocity. Ignore air resistance. How far will the cannonball travel before hitting the ground? How far will the cannonball travel before hitting the ground? Okay. So it's kind of the same thing that we did earlier, but now they're asking a different question. And also the angle is a little bit different. Let's see if we can steal any work from up above, because they say consider the same setup. Consider the same setup. Dimensional motion and advanced. Component. All right. Let me see if I can maybe just copy my drawing over. Let's do the lasso. All right. take this with me. Didn't need those green guys, but oh well. All right. Okay. All right, so same setup. Uh-oh. I want you over there. Uh-oh. Okay. Way in the wrong spot here. All right, right here, please. Here we go again. Sorry, it was my intention to do this in person, but I had to switch to online at the last minute, so I'm scrambling a little bit, but I think we can get it. Let's see. Is there a select? Type, paste. Ah, there we go. All right, great. So now this angle has changed. It's no longer 55 degrees, but it is instead 30 degrees. Okay. And I can see we're running out of time, so this will have to be the last one for sure. Hopefully I can at least help us set it up. So last time we were curious about the y direction, right? And we were curious how long it would take to hit the ground. Now we want to find out how far will the cannonball travel before hitting the ground? How far will the cannonball travel? So we need something that tells us the final position in the x direction. And obviously there's a combination of velocities in x and y directions, so we'll have to consider that. But if we're looking through your kinematic equations, hopefully you have the sheet ready for reference, look through those, and you're looking for something that you can solve for xf with, the final x position. If you're looking at those, you'll see that they all involve time in some way, or else you're going to need to solve for the time in order to find it. So we can kind of start with the same process that we did before. We find how long does it take for the cannonball to hit the ground? As they say, before hitting the ground, right? So we want to know how far it goes before hitting the ground. So that time is going to be the same. Once we do that, we're going to plug that answer in, and we're going to set that as the time. I'm speeding through this because we're wrapping up here. This is a great question for you to try and challenge yourself on what we worked on so far. So what is our equation that's going to give us the answer? If we know we want to find xf, starting from xi is equal to 0. So I'll just put a 0 there. The velocity in the x direction times the time that it travels, plus 1/2 the acceleration t squared, right? I'll write it. But what is the acceleration in the x direction? What is the acceleration in the x direction? It's none, right? There's nothing propelling us in the x direction beyond the initial launch. There's nothing that continues to change our speed. We're ignoring the air resistance. So this all just zeroes out. And all we need to do is find the time from the y component and find the Vx component. And you can break those up and you can do those just like we did in the previous problems. There's a problem for you to test yourself with. Test yourself. When you get through with that one, then you can try your hand at the final question here. Okay. Let me paste that in below it. You can pause and take a look at this one if you're feeling like you want to do another. And if you have any trouble with these, or you want to go over how you get to the answer in the end, since I didn't get to go over them with you right here, I encourage you to come into SV25 sometime when there's a tutor available, and we would love to work through these with you. We think they're very fun. There's the final question. You can pause it if you want to take a look at it. You can scroll back to the other one, and you can tackle that one as well. I hope that you got some good practice with vectors and you don't feel so uncomfortable using them. You'll use them a lot. You'll use them a lot. So they'll become more and more familiar, but it's good to practice as much as possible. That's it for today. I'll see you guys possibly in future workshops. Thank you for coming.